Want to do is a problem to do with inbreeding. So here I happen to have a single diploid biallelic locus. I have 20 homozygote AA, 1 heterozygote AB, and 30 BB. So clearly this population seems to be off, so I could even ask you to test this for Hardy-Weinberg equilibrium. Refer to the first problem that I already did for you to be able to figure out something similar. Okay, so we're not going to do a test of Hardy-Weinberg in this case, but instead I'm going to ask you, how do genotype frequencies and allele frequencies change after one generation of genotypic inbreeding? Okay, so in other words, AA individuals only mate with AA, AB with AB, and then BB with BB. And we've derived the formulae for how allele frequencies and genotype frequencies change from one generation to the next if this population is indeed inbreeding. And so let's write those formulae out. So after one generation of genotypic inbreeding, the AA genotypes would be present at frequencies p squared plus pq over 2. The AB heterozygotes would be present at frequency pq. The BB homozygote would be present at frequency q squared plus pq over 2, right? So in other words, the heterozygosity is halved, and then that remainder, that heterozygosity that's been halved, goes to both the homozygosity. So in other words, heterozygosity goes down, homozygosity increases after every generation of inbreeding. All right, so now all we got to do is compute these numbers. But in order to compute these, first we need our genotype frequencies, or sorry, your allele frequencies. Oh, by the way, let's write the formula out for the allele frequency changes, or in this case, no change, right? Because even though the population is inbreeding, while the genotype frequencies will change, the allele frequencies would be expected to be the same. And so A would be present at frequency P, B would be present at frequency Q. All right, so now we need P and Q in order for us to be able to solve this. We can easily compute that. The frequency of the A allele in the teeth degeneration is just P, which is given by, in this case, 2 times 20 plus 1 times 1 divided by, in this case, 2 times 51, which happens to be 41 over 102, which is 0.4. All right, so this is 0.4, which means that Q, which is equal to PT of B, happens to be just 1 minus P, which is just 1 minus 0.4, which is 0.6. So these are your P and Q values. All you got to do now is to compute these by plugging in the values. So let's do that. So you got PT plus 1 of AA is just P squared plus PQ over 2, which is 0.4 the whole squared plus 0.4 times 0.6 divided by 2, which is equal to 0.134. So similarly, the frequency of the BB allele, or BB genotype, sorry, is going to be Q squared plus PQ over 2, which is equal to 0.6 squared plus 0.4 times 0.6 divided by 2, which is equal to 0.48. Now you can either do the math to do the genotype heterozygote frequency, or you can also just directly compute it by subtracting these two from 1. In this case, it's just easier to do the math, so there's just 0.4 times 0.6, which happens to be 0.24. Now again, sanity check. You can add these three, and they should add to 1. If they don't add to 1, something's off. So you got to go back and check your math. Okay. How about allele frequencies? These two just stay the same, and so after one generation of inbreeding, these would just be expected to be 0.4 and 0.6 respectively. Okay. Again, important thing to remember are these formulae, so make sure that you guys put that in your concept list, and that's it.